No, witam Was wszystkich po krótkiej przerwie. Chciałbym ogłosić, że kod numer 2 i kod numer 4 zostały rozwiązane, także pozostała Wam 1 i 3. Warto VPS od Jakuba Mrygalskiego, od Mikrusa, polecam, na cały rok możecie dostać. A teraz na scenie wystąpi Patryk Wlazłyń.
All right, so today I'll be talking about low-cost silicon-based semiconductor manufacturing at home with the emphasis on being low-cost, like cost-effective. And before I begin, I want to say that I do not represent my employer, and I do say that because it happens that I work for one of the major semiconductor manufacturer, and this is not any work that I do for them. This is my personal stuff that I've been doing with a small team on our free time. And we do not have a chemical engineering background and anything related to it. We are mostly software engineers, and we are just hacking things around and trying to make semiconductors by learning about it. And the presentation is very complex. It touches a lot of complex topics, and I will not have enough time to go through everything. So it will use heavy simplifications throughout the presentation, but I hope you can learn something from it. Chemical stuff is mostly mentioned to justify the engineering part that we are doing, and I'm happy to answer any questions after the presentation if you, I don't know, want to know more about the software or actually chemical stuff. And before actually we begin, I want to recognize two people, Sam Zeluf and Jerry Ellsworth, which were doing the semiconductor research, like manufacturing at home actually before. And these two people were very important for us, and they basically were the reason why we started it. And let's start with a quick intro into semiconductors. This is the silicon wafer that we'll be doing all these semiconductors on. It's usually kind of glossy substance, a solid substance, usually polished, looks like a kind of a mirror, and it comes in different forms, but usually it's kind of like a disc. And this is the example of the finished wafer that will come out of semiconductor fab, and it's actually it already has some kind of digital logic implemented, and maybe a little question to the audience if anyone knows what kind of chip this is. You can tell after the presentation or something. There's no prize, but well, you can get some recognition, yeah. So let's begin with the introduction. So silicon itself is not really a conductor, it's an insulator, but we can make it a conductor by introducing some impurities. And for example, here we can see adding a boron atom to a silicon structure will introduce a hole here in the near the silicon atoms. The boron will connect with the silicon atoms, but it will have a 1 electron less, creating this hole that will be able to later attract different electrons, creating a carrier mobility. And similar thing happens with the phosphor atoms. They can be added to introduce an extra electron on the outer shell, creating a so-called N-type device or N-type conductor. And with the boron, we call it a P-type device or P-type conductor. And using this principle, there's an interesting device that is called a diode, and it's where the two places, the P and N-type, meet, and they will create a depletion zone in the middle, because from the N-type of device, the extra electrons will fill the holes on the P-type device, and in this small region in the middle, they will cancel each other out basically and create this isolation layer that will not allow any current to flow unless we apply the voltage to the negative side. So in the middle, we will have a depletion zone that can be broken, but only in one direction. And this is where the interesting part of this device comes in. So if we apply a negative voltage to the N-type terminal, we will be able to push through the barrier, but if we connect this other way around, we will actually widen the gap and make the semiconductor not conduct any electricity. So this is a kind of one-way switch. You can conduct electricity one way, but it will not conduct in the other direction. And another interesting and very core device in semiconductor manufacturing is a metal oxide semiconductor field effect transistor, or MOSFET for short. And it's a two diodes connected back to back, basically. And they will form a NP region, and the depletion zone here near the N region, and also here. And it has three main, let's say, inputs to the device, and it is a source, gate, and a drain. And when we apply a voltage between a source and a drain, because of the depletion zone here at the ends, it will not allow any current to flow. But there is a interesting trick. By introducing more positive voltage on the gate, we can attract more electrons from the source, and they will be attracted more and more if we even more positive voltage on the gate, and it will at some point form a channel region that will allow actually electrons to flow from source to drain. And this device can be used, it can be used like kind of a switch. So if on the gate we don't have any positive voltage, we don't conduct any electricity between source and drain, and when we put the positive voltage on the gate, it will start conducting electricity. And it turns out that this is very useful for building computers and all sorts of electronics, and this is what basically everything we use digitally has underneath. And this is the example of implementation of the AND gate on the NMOS transistor using three transistors. And let's go quickly through the logic, how it works here. Let's say we have an input A and B, and F it will be the output of the function. And if we apply a 0 and 0 on both A and B, let's follow how the current will flow. So the current will flow in both this direction and this, and it will hit this gate. And because this is the 0, this will be closed, and so no current will flow to the bottom here. So it will enable the gate, and we will apply the positive voltage on the gate. On the other hand, this will go here, and because the gate was supplied with the positive voltage, the transistor will be opened, and the current will flow through the transistor to the ground. And because it's grounded, the output reading will always read 0, because, well, the current prefers to flow here to the ground. But on the other way around, if we set a 1, we will enable this transistor, we will allow current to flow here, but it will be blocked on the next transistor. And only if we set both to 1s, this will be shorted to the ground, causing this previous signal. Now, well, this signal will go here, will be grounded, and no longer enable this gate. It will no longer enable it because there is a much more attraction towards the ground, and the current will not flow here, not enabling this gate, and therefore the 1 will be read on the output. So we will always see a 1 on the output only if both of the inputs are 1, and in other case we'll see a 0 on the output, which essentially implements an AND gate. And you can implement with the similar logic on the other gates, and basically you can I guess pretty much understand how to make a logic device based on that. This is the one more step that is needed to understand basically why the semiconductor manufacturing is useful, and it's a patent from 1959 by Robert Noyce, which actually showed that this small one MOSFET that I was showing on the previous slides can be actually made on a single wafer. You can make a lot of them and connect them in a special way using the insulators and doped regions to create basically any electrical circuit on a single wafer. So the only thing you need is that you just have to modify the wafer in a certain ways, in a certain places, and then connect the places in the right way to basically get a implementation of the electric circuit on a single silicon wafer. And this is the chemical process that we'll go through and will be a core to this presentation. What has to happen to actually make a semiconductor? So let's say we start with the silicon wafer, and we want to grow a insulating layer in the furnace. We'll go throughout the slides. I will show you all the tooling that is needed. Right now, this is just to understand how to basically modify the silicon wafer to introduce some impurities only in the certain places. So first we grow an insulating layer on the top of the wafer, and this is done basically by raising the temperature and waiting for silicon to grow the silicon dioxide. It actually it creates it very naturally. Then we spin something called photoresist, and it is a chemical substance, usually a liquid, that you can put on a wafer, and when you shine a line on its photoresist, it will be later you will be able to wash it out, basically creating these openings in the wafer, and these openings can be later used to use another chemistry like HF to etch the silicon dioxide, and we will get something like this. So we have a silicon wafer that had a silicon dioxide on top, and there was a photoresist that was washed off by shining UV light on it. And when we have something like this, then we have in this example, acetone bath to clear out the photoresist. And later we can use, for example, phosphoric acid, something with a phosphor in it. Phosphoric acid is actually easy to use because it's a liquid, and we can again very easily put it on a whole wafer. And when we do it like this, we can use again a high temperature in the furnace to drive the atoms of the phosphor into the silicon by simply applying the heat. And the phosphor atoms will go into the silicon wafer as well as the silicon dioxide layer. But if we are using, we can etch the silicon dioxide again using the HF solution, for example, leaving the silicon wafer to be doped only in these two regions, creating two n-doped regions. And a similar process can be used from a boron process to introduce a p-type impurities. And now we just have to regrow the silicon dioxide layer just to create an insulator to finish up the MOSFET. We basically follow the same steps as we did for previous steps to create these openings. And having the MOSFET or wafer in this state, we'll basically essentially create a MOSFET having two n-doped layers with the diodes and the gate that is separated by silicon dioxide, not allowing any current to flow from gate to source. The silicon dioxide is an insulator, and will allow us to basically implement a MOSFET. So this is the whole chemical process that is needed. And for the rest of the presentation, we'll go through how this is implemented and can be implemented cost effectively at home. So first, how to grow in insulating layers. And we'll be growing in silicon dioxide. And you can grow it by basically sticking the silicon wafer into high temperature. And silicon dioxide will be formed by silicon grabbing oxide atoms from the air. So you just have to raise the temperature and basically wait. If you want to do it faster, actually much faster, you can also pump a stream of deionized water. It will probably vaporize at this point in these temperatures. And for some reason, having water molecules in the air instead of just using the dry air makes the process much faster. So the growth is much faster. And this is how you detect if your wafer has any silicon dioxide on top. This is a very useful thing for a silicon dioxide, is that for different thicknesses on the x-axis, we will see a different color with our basically naked eye. You can look at it and basically guess what kind of thickness you have. And different thicknesses are used for different purposes. For example, you can use the silicon dioxide just for an insulating layers between the silicon wafer and the phosphoric acid I was showing on the previous slide. But it will be at the end also used for a gate. And you can basically control how much voltage you have to apply to the gate by controlling how thick the oxide is. And this color pattern works because when the light shines on the wafer, some of the light actually bounces off of the silicon dioxide, but some of it comes through and actually bounces off of the wafer substrate. And when the waves come back, they will interfere with each other, creating some kind of, let's say, illusion to the human eye that the light was actually colorful when it comes in, but actually it's an interference pattern. But it's useful to assessing how thick the oxide is, because the thicker the oxide, the different the shift and the color will be, basically. This is the example of the silicon wafer that has a pattern with two different colors, two different thicknesses of the oxide. You can, I guess, can see with the naked eye that there is two thicknesses of the oxide on the wafer. Yeah, and other examples. And this is, yeah, if you grow an oxide on the whole wafer and then kind of, well, not wash it like entirely, you will see this kind of rainbow pattern that looks cool, but doesn't really is not really useful. When you see this when manufacturing chips, it's bad. It's basically you don't control how thick the oxide is, and it's basically bad, but it looks good. It looks cool. Yeah, and this is another example. All right, so we are starting with the tooling that is needed to do this. So we'll start with the high temperature furnace. And the furnace is built with the fire bricks. They can withstand something like 1500 degrees C temperatures. The heating is achieved by using the resistance wire, and basically, yeah, if you do a current flow through the resistance wire, it will heat up and give out the heat. And we will supply a water by a quartz tube through the water pump, and there will be a vertical opening in the furnace, and temperature control and water supply driven by Raspberry Pi Pico. You can see the quartz tube. I'm not quite sure if this is really seeable, but there is a quartz tube from the top, and water pump will pump the water through this, creating the water vapor that I was saying previously. This is the simple circuitry that is driving the furnace, the heating. This part on the right is not really that interesting. This is basically a fan in the power supply to not make it melt. But what's interesting is this SSR, which is controlled by 3-volt logic from the Raspberry Pi, and when the GPIO basically is turned on, the power supply will draw power from the socket, 230 volts, and will basically conduct it through the resistance wire, which will heat up and make the furnace reach certain temperatures. And SSRs are cool because we can control them with the digital logic 3-volt, and we can switch at 330 volt current, right? And yeah, and SSRs are cool because we can implement a pulse width modulation by switching very fast on and off, this thus controlling how fast or how aggressively we heat. This is another part of the circuitry. This is the water pump. Basically, it's connected to VCC and grounded via NMOS transistor. And NMOS transistor is opened on the gate from the microcontroller. So if we want the water to be pumped into the furnace, we basically open a GPIO that is steering these NMOS transistors, and the DC motor will start pumping water into the furnace. So pretty simple stuff. And now it goes into doping, so introducing the impurities like phosphor and boron into the silicon. This is the example process for phosphoric acid-based process, chemical basically. So you use silicon dioxide as a dopant isolating layer. So if you don't want to dope in a certain regions, you just grow a thick enough oxide that it will stop any doping. You do an optional double oxidation, which is a process I will describe if we have some time left at the end, but for now let's leave it at that. Then we use kind of spin coating. So the phosphoric acid is a liquid, but we want to create some kind of uniform layer on top of the wafer, and we use a spin coating for it. So it basically is placing a wafer on something that spins really fast, and it turns out it will create a very reasonably reasonable layer of the phosphoric acid on the top of the wafer. And for spin coating, we used a computer fan, like 12 volt for computer fan hacked around, and it works great and is very cheap. For better adhesion to the wafer, we dissolve hydrofluoric acid in butanone, alcohol, 1:16 volume ratio. We found this trick on one of the papers, and it works great. And we also hold a wafer before we spin on it. We hold it on under the butan flame for, I don't know, 20 seconds or something like this, and it improves the adhesion to the wafer as well. So these are like 2 tricks we found on the internet, and it works great. Now, so the doping process is involves also some kind of cleaning, and we use sulfuric acid for it. So first we begin with the sulfuric acid bath. It will remove all the organic residue. Then we do some kind of acetone bath and isopropyl bath that will remove the acetone residues. And when we have a cleaned wafer like this, we put it on a butan flame for around 20 seconds. And we put it on a spin coating with the phosphoric acid solution I was mentioning on the previous slide. We spin it by supplying 11 volt to the computer fan for 20 seconds. And then we put it on a hot plate for a pre-deposition. And this step is usually used to vapor out basically some chemicals that are liquid and are not needed, like a butanone or and the butanone from the phosphoric acid solution we have. But it also makes all the substance harder, and it will no longer be a liquid, and it will form like a very thick and hard layer on top of the wafer. And then when we have this phosphoric acid based layer on top, we can put it in a furnace for 930 degrees C. And first we put it for 15 minutes when pumping water, and then 45 minutes doing it dry. Maybe we have some more time to talk about why we do this way, but let's leave it for now. And then we put it in we are etching it in the HF for 4 minutes, depending on the oxide thickness. So the bigger the thickness, the longer you basically have to do the bath, but HF will eventually etch all the oxide. And this is the hot plate that we've built. It's basically it's similarly built like a furnace. It has a brick, 2 bricks basically on the base. It has an aluminum plate on the top, and beneath is a resistance wire. So basically the setup that we have for a furnace. Oh yeah, and there is a temperature sensor here, PT100, that is constantly reading the temperature, so the Raspberry Pi can enable and disable heating to reach the target temperature. So again, we build this with fire bricks, and we have a resistance wire and aluminum plate on the top. We reuse basically the same code for the Raspberry Pi that we have for the furnace because, well, it's mostly the same. It's just different configs. We take it from, we have different files for different devices, but the firmware is the same. You just enable different configs. And this is the picture of it without the aluminum plate. It's basically, as I said, it's a resistance wire and bricks. Or alternatively, this is how we started, is you take an iron and you take off basically the part that gets hot, and you can take these two cables, connect it to the Raspberry Pi through the SSR, and you can drive with pulse width modulation how much you heat. And we were able to do a actually working MOSFET using this technique. So, and it's actually cheap if you find some kind of old iron there sitting somewhere. Yeah. Although the hot plate works a little bit better. You don't have the temperature sensing here. We actually use the infrared camera to check how hot it is. Okay, and now we go into the photolithography process, which literally means drawing with light. And it's basically a way to remove a photoresist only in certain places. So we will shine a UV light only in certain places, creating some kind of a circuitry that we want to embed into the silicon wafer. And it basically works like this. So we have a substrate, in our case, a silicon wafer, we spin coat a photoresist on top of it. And later we will apply a UV light, and we will use some kind of mask to block UV in a certain places. And in the places that it was exposed to UV, we will be able to apply a developer, which is a different liquid, let's say, and it will remove the photoresist only from the places that we were shining the line through. Instead, in our example, we will not have a mask, and we will just use a DLP projector, and we will project a JPEG file. So basically, when we project a JPEG file, the black pixel will be equivalent to the mask, and the white pixel will be like a UV shining through. And this works great. You don't need any mask. You just have a DLP projector mounted, and you shine it on a wafer with the pattern you want to pattern. Yeah, so we are doing maskless photolithography. This is some kind of concept that is used in other places too. Using the DLP projector, the photoresist is an HF resistant, so we can use the chemical process I described on the previous slides for etching the silicon dioxide and not attacking the photoresist, so it will act like as a insulating layer. Places exposed to UV are washed away by the developer, and exposed parts of the silicon, actually silicon dioxide it should say here, can be etched away. And alignment, and when we have this photolithography step, you kind of have to align properly, so you know where you're gonna be shining on the photoresist. And we have a USB camera setup that I will show you shortly. But let's go through the chemical process first for the photolithography. It's kind of long, but let's go through it. So first we do a acetone bath to clear all the residues on top of the wafer. Again, isopropyl bath for 10 seconds. Then we spin coat a photoresist on top with the 8-volt supply to the computer fan for 30 seconds. We then do a soft bake on a hot plate for 100 degrees C. We then set up a DLP projector to heat for 45 minutes, and then we exposure for 1 second the wafer with the UV from the DLP. Then we put it on a post-bake, and it will create where we have not been shining the UV light, it will create a very tough structure, similar to how the phosphoric acid process works. And then we'll put in the developer bath, and the places when we were shining with the UV will be washed away by this step for the 60 seconds. Then we clean with the H2O, and again, vapor out basically any H2O that was left on the wafer. And then we do HF bath for 4 minutes. It actually depends on the thickness. If the thickness is bigger, we will have to do more. And then we clean the wafer in the H2O and basically do an acetone cleaning at the end. And we have and we would have this kind of wafer in this stage that has they washed away photoresist, and the HF will remove all the dioxide that I was showing on the basically I think second slide or something like this. This is the DLP mount. So this is a very simple setup. The DLP will sit on top of here. There is an opening that it will shine through, and we will put the wafers on the bottom plate here. So I have more pictures that will be actually showing this better. So we have a DLP projector on top, and we'll be putting the wafers here on the bottom plate. And you can adjust the plates with the screws, so you can easily find when the DLP is actually focusing the image correctly. Yeah, and you can see there is an opening for a DLP to shine through. The wafer would be here, and we have an USB camera looking at this all the time, so we can connect a computer and basically align a wafer to the proper place before we start shining. And yeah, and this is the real-world picture of it. There's a DLP, there's some kind of wooden stuff, and a USB camera here, and a Raspberry Pi connected to it. And from the side, it looks like this. There's a DLP, and there's actually a shutter too. So whenever the DLP is shining, it doesn't really look that good. But yeah, so we want to expose, as I said, for just 1 second. And to measure it properly, we have a Raspberry Pi connected to a motor that will spin this shutter, which is basically a circle with the 2 openings. One is blocking any light and one is open, basically. And so we will say to the Raspberry Pi to open the shutter for 1 second and then close, so we know that we are shining for the same amount every time. Yeah, and these are the pictures from the USB camera of the alignment system. This is the picture of nothing sitting in the on the second plate, and this is the wafer and not shining. This is when we are aligning the wafer, and this is when the DLP is shining, and you can all the time look at it from the USB camera. We also have a mode when we can create a background picture and save it in memory, and then apply live feed of the camera to the image that we saved, and we can apply some kind of alpha channel, so we can look what was the previous places we were exposing the wafer, the light to the wafer, in which place, and we can align it properly. Yeah, and this brings us to creating a contacts to the created impurities on the wafer. And contacts are basically something metallic connected to the source, gate, and a drain, allowing us to basically use the device by, I don't know, applying voltage and stuff like this. And we will do this. There are several things how it can be done. We are doing this with the silver-based glue. It's very cheap. I think it's like $1 per, I don't know, I think 5 millimeters. It comes from China, so you have to like wait a few weeks for it, but it's very cheap and it's very easy. The alternative, and this is how the big boys do it, is you kind of create a high vacuum system and you deposit a copper on top of the wafer by using a high voltage plasma, basically. And this setup, we actually started building it, but it's not really ready, and it's kind of expensive and hard to do. But you can like get away with just the glue from China, silver-based, and it works great. You just apply the glue, a little bit of glue, and then use hot air to basically to solidify it, and it creates a very good ohmic contacts and worked great for us. This is this is a picture of the MOSFET just before applying the contact, and I think I just put it because I think it looks cool. So this would be the gate, and this is the source and a drain. And this brings us to how we test, and I'm going to show you some results. So one of the tests that you can do to test how the semiconductor, if the semiconductor actually worked, if your process works, is by applying something called hot point probe. And it works like this. So you apply a amp meter or a voltmeter on the surface of the wafer, but one of the probes is actually hot, like 200 degrees Celsius hot. And whenever the probe actually hits, connects with the wafer, the wafer will actually expand, and when expanding, it will push away some of the electrons from this place, and they will move through the other end. And the other end will not push any electrons. And so when you connect a voltmeter between it, it will create a negative, this will be positive because we moved away the electrons from here, from the hot probe, and this will become negative relatively. And this way we can check that this is an N-type semiconductor, because if we do this for a P-type semiconductor, for example, we will have more holes here, so it will be there will be pluses, but hot probe will expand again the material, pushing away the holes, and it will create more holes on the other side for the electrons, and it will create actually a reverse bias. So by reading on a voltmeter the voltage, the difference in voltage, you can determine whether you have a p-type semiconductor or n-type. And so with this, you can determine whether your chemical process worked. Yeah. And another way of testing the wafer is using a 4-point probe test, and it's basically you apply the constant current on the outer of the 4-point probe test, and you actually measure the voltage in between. And so when you have when you know what the current you were flowing and what the voltage was measured, you can determine basically the resistivity, and the resistivity will you can basically derive how much or how well you doped the wafer in this place. And we had a 3D printer set up for it. We have 4 probes connected to the 3D printer that was going on the wafer, measuring for each place on the wafer how well it was doped by measuring this resistivity. But in practice, it actually doesn't work that good. This is the setup. So you basically have a current source connected to one of the terminals, and this other terminal will go to the power supply, and you will apply basically a voltage in between, a voltmeter in between, and you can measure the resistance. The problem is that we actually didn't get that good results, even though the setup looks very cool. For some reason, when you have a very low resistivity, the values that you're reading are all over the place, and we suspect that this is because we formed something called Schottky contact on the top, which actually creates a diode in itself when it's making a contact between a metal and a semiconductor, which screws up all the measurements. But maybe we have to maybe work a little bit more on it. We don't really have any good results doing this, although we spent a lot of time on it. And more tests, basically, or demos. I have the link somewhere here. It will be a solar cell demo. What's important? Oh yeah, this is another thing, another way to test if your N dopant worked, and it's because when you have a wafer and it's doped, like here, because there are more electrons here on the N side, and because there are less electrons here on the P side, when you're shining light on the N type, it turns out that it will actually give some energy out to the electrons, and they will move them out of the shells. And if you connect a minus and plus terminals to such thing, you will collect the electrons, getting the energy from the light, for example, from the sun. And so with this thing, you can basically test how well you doped for N and how many electrons you can collect by shining light on it. And I have a demo on somewhere here. Yeah, and you can see that I have a voltmeter connected measuring DC volts, and when I was not shining a light, we see some kind of very small value, but when we start shining the light, we can see a positive voltage on a voltmeter. And if I swap one more time, and when I'm gonna swap the probes, we should see the same basically voltage, but in another direction. And this is exactly what we see. So we have a minus here, but we still see a voltage. It's just flowing in the other direction because I switched the probes. And for comparing, there is a clean silicon that don't see this effect. So we can shine a line on it, and we don't see this effect. The voltage is basically staying near the zero. There is also a demo for the diode test, which is not very, I'm not sure if it's not very, it doesn't really look good there. So, but you have to believe me that when I connect it with the N and P in one direction, it will allow the current to flow, and in the other way around, it will block the current. And this is the thing I was saying when I was talking about the diodes on the first slides. And now we have also a demo of a MOSFET. And here we have a ohm meter measuring resistivity. Not sure if you can see it correctly, but it's a 5.2 kilo ohms between source and drain. And I have a probe here that I will apply a extra positive voltage on the gate with this red probe. And when I'm not applying it, we will see a 5 kilo ohm resistivity, but when I crank up basically the voltage on the gate, we should see this resistivity going down, and it in fact goes down to 4, 4.2, right, 3, and as I'm going up with the voltage on the gate, the resistivity should go down and down and down, creating this this channel between the source and the drain. And now we have something around 1.5 kilo ohms. When I don't take the when I take out the probe, we will see 5 kilovolts back, confirming that we have something that we can call a MOSFET. Although this characteristics is horrible, but it kind of works. Okay, we have some kind of not so nice setup, but it works. And also, when you have a MOSFET, there's another demo of the solar cell between the back of the wafer and, for example, a drain in this example. So we will again form a diode between a drain and a back of the wafer, and when we shine a line on it, we can see 300 millivolts of current, and when we don't shine, we see a 0. Yeah, and this is how you can basically confirm that your wafer, your chemical process for the wafers work. Okay, I think we were gonna wrap it up with the software. We have the software for Raspberry Pi. It's open source. We develop in the open, and we have a semi-open Discord server. We basically send you an invite if you are interested in the project and want to contribute. And there are a lot of people doing more or less or the work they have time on and they are excited about. So we have a Raspberry Pi Pico firmware that we actually share between multiple devices, as I was showing, for example, between furnace and a hot plate. We just have some config values that can configure the device and enable the drivers and some kind of settings. This is the example of the command line. We have a command line access via the Wi-Fi and a USB. So user can so the Wi-Fi will connect to the local network, and user can access it via Wi-Fi, or it can connect with the USB and connect to the command line, which allows to, I don't know, reboot device, set the pulse width modulation between 0 and 50 to say how fast we're gonna be hitting the furnace. We can set up the target temperature and enable the auto steering into the target temperature, and Raspberry Pi can drive it by itself. And yeah, we have some auto. We can enable the water and how fast it will pump into the furnace, and some other options. Yeah, and this is the example of the status line here at the bottom. We're gonna skip the code a little bit because I see I don't really have much time. So this is the example of the status line. We have a current temperature, 932 degrees, out of 930 requested as a desired temperature. Right now we are sitting at 21 PWM level, at max 35 and total max 50. This 35 is actually settable at runtime. This is the like a absolute maximum of PWM value, and we are sitting at auto steering of the furnace. Yeah, and I'm gonna skip the pulse width modulation configuration because we don't really have much time on it. And we have a custom algorithm. We actually started with the PID controller for the furnace, but it actually worked not very well. So we have our own custom algorithm for it. We basically, what we do is we calculate the deadline, and this is basically we calculate the time when we have to go and check whether the temperature is actually rising in the direction that we want. And this is the whole algorithm basically. So what this code does is basically checking if we are going in the good direction, and if we are going in the wrong direction, or going in a good direction, but very slowly. So let's say right now I have 200 degrees C in the furnace, but I set it to be 600. So I'm checking if we are going in a good direction. So if we are going in the wrong direction, or we are going in a good direction but slowly, we just nudge the PWM into the direction we want to go. So if the temperature is too high, we will basically subtract, because we will add a -1 here. It's not very that interesting, but I wanted to mention this. We also have a way to pre-compute a table for each PWM level to say what is the terminal temperature that can reach on a given PWM and drive the furnace with this. So for example, here we'll have for the PWM level of 4, we can see that the terminal temperature that we can reach with this level is around 200 degrees C. So we know that if we want to reach 200 degrees C, it's probably good to just set PWM to 4 and basically wait. So this is another way of steering the furnace, and it works better than PID. Temperature measuring works by using the thermocouple, and the thermocouple works like this. So it works similar to the hot point probe test. It's basically a long wire that is stick into the furnace and connected to the microcontroller. And when the piece of metal is actually near the heat source, it will draw out it will move out the electrons from the metal, causing a difference in voltage, basically between the ends. And you can measure this voltage and compute the temperature of the furnace with this effect, and this is called the Seebeck effect. I'm sorry that I'm rushing a little bit, but we're running out of time. And there is a simple SPI interface for the driver for the thermocouple we are using. The main point here is that for the initialization, you just do 2 writes on the SPI, and later reading the temperature comes down into 1 SPI transmission and shifting the values from two registers to form a temperature. So it's very simple setup. You just take a driver and a thermocouple, and you can measure high temperatures between like 0 and 1500 degrees C. We do have a lightweight scheduling because we have a lot of work like TCP and some other driving of the furnace. And we basically initialize all the tasks that we have to do. And in the main loop, we just go basically through each task. And if the task doesn't have any work, it just returns immediately. We don't allow it to block. We just check if we have some work to do, and we do it, and we return to other tasks, basically. So if there is some kind of TCP packets that we have to respond to, the TCP work will do it. If there are no packets, it will return, and we will check if we have something to do for the other tasks. So it's a very light scheduling. We write on a bare metal. And for the future, this is the very last slide. Right now, we are working on a better photolithography stepper. So this DLP system that we have, it actually lacks some kind of moving piece that it can move the wafers and project the images with the higher resolution. And this is what we are working right now. We want to do a setup for metallization with the high vacuum and high voltage and plasma coating with the copper. And this is what we are working as well. We're also working on the chemical process for better spin on dopant, better spin coder, that we can actually measure how many revolutions per minute we are doing instead of using computer fan and saying that we are rotating at speed of 11 volts, right? And we're also working on a CMOS project. This is basically another way of creating semiconductors. It's actually have improved characteristics, but we don't really have time to go into it. And there's an interesting thing to do a laser doping. You can skip most of the steps, and you basically can apply the heat by shining laser on the places on the silicon wafer where you want to dope, and removing all the furnace and other steps. And this is also an interesting thing that we wanted to explore, but don't really have any results yet to say more. And this is pretty much it. So thank you for attention, and I'm waiting for questions. Maybe there are some.
That's a tricky question. Where do you obtain the base silicon wafer from, and HF acid?
Yeah, right. So the silicon wafers, so first we wanted to make them ourselves. There's a Czochralski method to make the wafers, but it's kind of rigid. And we actually went with asking our friends from China to ship the wafers to us. So we actually buy them. They're quite expensive, but not that expensive. So the single wafer, when you just buy a single one, it's like 400 zlotys. And if you buy 25 of them, it's like 2,000 zlotys. But 25 wafers is a lot of wafers. So it's like you're probably not going to use it very fast. So.
if it's cheap, can I pay you and will you deliver me ready one?
A single MOSFET, sure. The characteristics are horrible, by the way, but it's we are actually working on it just for half a year on this project. So these are very early results, and we'll like to do some more chips and something like Sam Zelov was doing. And yeah, we would like to do some kind of working chips, very small ones, but this is not what we have here. So yeah.
I might have missed it, but how much does the manufacturing cost total and how much time it takes?
Yeah, so the time for a single silicon wafer from the beginning to the end to get a MOSFET, it usually takes like 12, maybe 16 hours, so it's a long time. But and for the how much it costs, I think we actually made it under 3,000 zlotys. If you're interested in a single wafer and basically doing a single MOSFET, you can experiment with it in a range of 3,000 zlotys easily, including building the furnace.
What's the smallest size of transistor you can make yourself?
Something around 1 millimeter, but maybe we can do it smaller. We just can make it in 1 millimeter feature without really much work. It will not be that hard. We actually did some tests with photolithography, and we can easily pattern this small features.
Which PWM driver on Pico do you use? Is it stable?
We are using the hardware driver. I think they only have one. It is stable and it works good. We actually tested it with the logic analyzer. I don't know, it's a hardware one that comes with the Raspberry Pi.
Initial slide looks like it's a paper. Is it available?
The first one looks like what? We got accepted on one of the conference. It's a Yashowitz conference, and we will publish a paper on it. So yeah, keep tuned, I guess.
And the last question, what is the lithography of the circuits you have produced?
So you're asking about types of the circuits. I believe we only did MOSFETs because this is what we actually wanted to test. But we are in the we're trying to make some kind of logic gates that we can connect together. We are kind of blocked with the metallization step, and this is what we are working on now. But a lot of MOSFETs and a lot of solar cells. This is what we've done. Yeah.
Okay. Thank you.
Thanks.